Okay, thank you very much. So I'm posting to the chat the link I just opened now. Essentially, is the abstract of my talk or my tutorial. Okay, so I'm using a Jupyter notebook that is available already on the server, but in case you are not using the server, then you need to download the tutorial, this one. Okay. So let me go on the server. So you should have the tutorial in your directory. It is called Giacomazzo _ Einstein Toolkit _ 2021 _ ATK 2021. Okay, so we can open it. Let me see if I can keep the chat open. So, okay. This notebook, of course, assume that you already follow the tutorial from yesterday, so that you have the Cactus installation working in your server. Okay, because we are going to use the Einstein Toolkit to read some initial data produced with LORENE. Okay. Before starting, I want to thank, by the way, Joshua for the very nice overview of how to solve initial data problems in general relativity, and a tool for the overview of how to use LORENE to compute initial data for binary neutron stars. Okay, I hope you were all able to open the notebook. Okay, so the first cell is just something that is convenient for us in order to use the notebook, nothing special here. In the second, I just make sure that I'm in my home directory. So in my case, it's /home/bgiacomo. And the next thing we need to do is, of course, to download the initial data. So the initial data is also available on the page of my abstract. And what we do here is just to download them. They are contained in this tgz file, so it's a compressed tar file. So we are going to execute this file in order to download this file. Okay, it should be very quick because it's a very small tarball. Next step, we are going to decompress the tarball and extract all the files. I see the question in the chat. Yes, this is the same initial data we're supposed to generate during the last talk. I'm not sure about the separation and the masses. These are not completely sure. It's the same equation of state. So we expand the tarball, and essentially you will see that you should get a directory called ETK _ school _ 2021 with a lot of files inside it here. In particular, the file that contains the initial data is the file called resu.d. Okay, so for example, if I do ls now, I should see that in my home, I have the, where it is, the ETK _ school _ 2021 directory. In that directory, you will also have all the configuration file that you need in order, if you want to try to regenerate this data by yourself using the init bin and the call executable from LORENE. In particular, you should have, here they are, the par _ EOS parameter file, par_EOS2. There should also be the par_EOS1. It is with the equation of state. We are going to have a look at this. And then you also have the par grade 1, par grade 2 that I tool described before, par init, and par call. And I think it is all that you need in order to generate the data. So inside this directory, you also have all the parameter file in case you want to try to generate the data yourself using init bin and call from LORENE. When you do that, as I said, you get a binary file which is called resu.d. And so what we want to do now is import, read this data within the Einstein Toolkit. The first thing that we need to do is to have a look at the equation of state. In this case, we decided to keep things quite simple and therefore to have a piecewise polytropic equation of state. So we are going to have a look at the content of par _ EOS1.d, and this should be identical to the one that Atul was showing before. So let me execute this cell. And you see the content of that file. As Atul told you, you have the type of equation of state, which is 110, which means piecewise polytropic equation of state. you have the number of pieces, 7. In particular, these are something like 3 for the core and 4 for the crust of the neutron star. This is the standard number of pieces that is described in the paper by Jocelyn Reed and collaborators 2009. As I to describe, you have the array of adiabatic index for each piece of the piecewise polytropic. You have the array of usual densities, and then you also have this value, which is the first polytropic constant for the segment at the lowest density. You don't need the others because by imposing that the pressure is continuous between the different segments, of course, you can find a relation, and from this first kappa polytropic constant, you can derive all the others. More details about this can be found in the paper by Jocelyn Reed and collaborators 2009, where piecewise polytropic equation of state were introduced. So what we need to do now is to convert this number essentially in something that can be passed to EOS omni, which is the equation of state driver that is used by the Einstein Toolkit, and that is going to use geometric units. Okay. So I took this conversion from a tool. I think there were also described in the slides, if I remember correctly. So these are the same conversion factor that the tool also was mentioned in this slide. I don't think actually had time to show this. But anyway, we need to convert essentially the polytropic constant, for example, in the low density part from the units used by Lorene to the units used by Cactus. And this is what we do in this step. Okay, so I define K0 underscore CGS as the first polytropic constant or the first piece at the lowest density. I wrote here in the comment. This is in CGS units. Here we have the conversion factor from Cactus units to CGS. And then we have the gamma, the adiabatic index, again, of the lowest density region, because we are going to need this in order to convert. So let me execute this so that we define these variables. And here are the conversion that you need to execute in order to go from CGS to Cactus units or vice versa. So what we are going to need is this one. So we want to go from the polytropic constant in CGS units to the one in Cactus units. And this is the expression we need to use. And this is what we're going to do in the next cell. Okay, so we get essentially that this 6.8 times 10 to the minus 1, this one, which is the polytropic constant for the lowest density part of the piecewise polytropic equation of state in CGS, corresponds to 168 point something in Cactus units. Okay, so in units in which the speed of light is equal to 1, the gravitational constant is equal to 1, and the solar mass is equal to 1. And this is the first piece of information we'll need in our parameter phi, because EOS omni, which is the driver for the equation of state that we are going to use, needs in order to compute the pressure. The other thing that we need to know is, of course, the density that separate each interval in the piecewise polytropic equation of state. So in the case of the par EOS of Lorene, you get this again in a logarithmic scale in CGS units, so gram per cubic centimeters, and we want to convert them in Cactus units. So what I did here was just to get those values. So I just copied essentially the values you get in per EOS. Okay, this is the logarithm base 10 of the density in CGS. So what I created was just an array which I put 10 to the exponent of the different numbers we have here. Okay, so 10 to the 7, 10 to the 11, 10 to the 12, 10 to the 14, 10 to the 14.7, 10 to the 15. This is what I did here. Nothing really special. So these are still essentially the value in CGS, so in gram per cubic centimeter, that tell you essentially in which region of the piecewise polytropic equation of state you are. And now we want to convert these values into CGS, and this is the following step. Okay, so we are converting from CGS to Cactus units. So these are the values that we need to pass to the Einstein Toolkit to tell essentially the toolkit, look, we're going to use a piecewise polytropic equation of state with 7 pieces. Each region is separated by the following one by these densities in Cactus units. And we also computed before the value of the polytropic constant in the lowest density region. We don't need the other one because, as I told you, this can be easily computed by just imposing that the pressure is continuous from one interval to the next one. The other values that we will need are the adiabatic index, but these are adimensional, so we don't need to do any conversion for them. So these we can just copy and paste in our parameter file. Okay, so these are the 7 adiabatic index that we'll just copy and paste in our parameter file because these are adimensional, so there is no need for conversion here. So now we have all the things that we need to do. So as I said, this notebook assume that you already have Cactus inside your directory because I assume you followed the tutorial yesterday in which you installed Cactus on your server. So I go into the Cactus directory now. Okay, so in my case, home, Giacomo Cactus. And now what we want to do is just create the parameter file in order to read this initial data. In order to be able to run on this server, the parameter file we're going to use is quite simple. It's going just to read the initial data, produce an output, and then stop. That's it. There is no evolution going on here because in order to do an evolution of binary neutron star system, you typically need to run on a cluster. Possibly, if you're using very low resolution, you may be able to do a very simple evolution, maybe on a powerful workstation. Like if you have a workstation with 32 GB of RAM, or even better 64, you can, I think, run an evolution with a very low resolution. But it is something that we cannot do on the server. So, as you should know from yesterday, this is the typical structure for parameter file for the Einstein Toolkit. So you have the list of thoughts that you want to activate. In particular, the thought that is important to us are, of course, EOS Omni, the equation of static trivial. And then we will also use GR Hydro, which is the tool that you can use, for example, to evolve this data. But as I told you, we will stop at iteration 0. And then the term medon underscore bin underscore ns. This is the term that actually reads this resu.b binary file that is produced by Lorene and import the data on our Cartesian grid inside the Einstein Toolkit. Okay, here we have some. I'm not going to go through all the parameters because it will take too long. This is just something that is to output. We can skip. And these are just some output that is done. Just wanted to point out that, as I told you, this file is going to produce the output. In particular, you're going to have a 2D output, which means, for example, the rest mass density on the equatorial plane as well, which means the XY plane, as well in the XZ and YZ plane. This is something that then later we are going to visualize using Qubit, for which, by the way, there will also talk after me. And it's also going to produce some 3D output. Okay, we can do this because the resolution we're going to use is very low, so the files will be very light, and so they will be very easy to open them. Let me go on, we can skip this. Okay, the first thing we need to do is to tell the term medon bin ns where the initial data are located. Okay, so in our case, we downloaded, if you remember, the tarball. We extracted the files in tarball, and so in our home, we have this etk underscore school underscore 2021 directory, and that directory I showed you, you have this resu.d file. Okay, so in my case, I'm telling medon bns that the file are located in home, Giacomo, etk underscore school underscore 2021 / resu.d. In your case, probably you will have home / your username and then the same. Okay, so you may want to modify this, putting here your username. Otherwise, possibly it should work, I think, anyway, because I think my directory is readable. But in principle, of course, here you should put the location of the initial data file where you have that on your machine. Then we are going to define the grid. To simplify a bit the parameter file, I'm applying reflection symmetry along the z = 0 plane. So we're going to evolve only the part of evolve. As I said, we just read the initial data and we stop. So, but we were going to have a grid that include only the positive z part of the domain. The domain is very small. In particular, we're going from -30 to 30, both in x and y. And to save a bit of memory, we are going from 0 to 12 in z. And the resolution is pretty coarse, 0.3. All of this is in solar masses, so this is approximately 450 meters. It's a very, very coarse resolution. Typically, if you want to do a reasonable evolution with this kind of data, you may want to use a resolution inside the neutron star of around 0.12. And of course, you want to use a domain that is much larger than this, because possibly you want to avoid any possible contamination from error that can come from the boundary, and as well you want to extract possibly gravitational wave signal. But in this case, we are just interested in reading initial data, print the output in order to check that the data was read correctly, and that's it. And then we're going to stop. So this is fine. Okay. For example, you see here that they put the final time 0, which means essentially it's just going to read the initial data and then just stop. Okay, for the rest, we can skip. Okay, still related to initial data. So in HydroBase, we have to specify which term is going to set the initial value for the hydro variables for rest mass density, specific internal energy, velocity, and so on. And we are going to say that these initial value for the hydrodynamic quantities are going to be provided from Bedon_bin_ns. Let's go on. If you do an evolution, in this case, I'm going to use McLachlan. As I say, we stop at 0, but it's important also to tell ADM base who is going to set the initial data for the metric. Okay, so here we tell HydroBase who is going to set initial value for the dynamic quantities, Bedon, bin, and S, and the ADM base want to have the same information for the metric, and so we say that essentially the metric is set by, and also the extrinsic curvature and other variables are set by Bedon_bin_ns. We also set the initial lapse using Bedon_bin_ns. And as Joshua said during his talk, you are not forced to keep essentially the same lapse and safe shift that is coming from the initial data. This is something you can change. And usually when working with binary neutron star data generated with LORENE, we found that it's very convenient actually to initialize the shift to 0. Okay, so instead of taking the shift vector coming from LORENE, we just initialize the shift vector to 0. As far as I remember, this is something that we did in the past to reduce coordinate eccentricity, if I remember correctly. So this is just a trick that I suggest to follow. So to take the lapse from Bedon_bin_ss, but set the shift to 0. Can go on. I don't think there is anything else particularly important here for the reading of the initial data. And now we have the equation of state. And here is where we're going to put the values that we converted before, okay? Because essentially we are going to read this data from LORENE, but then we have to tell the Einstein Toolkit which equation of state it's needed in order then to compute the conservative variables and then also to evolve the data. So we are going to use EOS Omni. As I said, this is the standard equation of state driver for the Einstein Toolkit. We are going to use a piecewise polytropic equation of state with 7 pieces. Okay, as I said, 3 are for the core and 4 for the crust. This is the same number of pieces we had in par_EOS1.d, so the ones that were used to generate the initial data with LORENE. The first thing we need to provide is the value of kappa, the polytropic constant in the lowest density region, and we computed it before. It was 168 point something. I just copied and pasted that value here. I need to provide to EOS Omni the value of the adiabatic index in each of the region. And so, as I told you, the adiabatic index luckily are adimensional, so I just copied and pasted the values that we have in par_EOS1.d. Okay, if I go up again, where we did the cut. Okay, so this is the array. Okay, I just copied and pasted this array of adiabatic index in the parameter file because these don't need any conversion. And here they are. And then we need to provide to EOS Omni information about the value of the density that divide each region of the 7 pieces. And again, we have to provide them in cactus units. And so here I'm just pasted the values that I converted a few cells above. So now I specified the equation of state in Iosomni as a piecewise polytropic equation of state with 7 pieces. And is identical to the one we use in LORENE. The reason for which hybrid ROM has only 6 values, because these are the 6 divided densities. So at the end, you have 7 regions. You have one region, which is the region below the density 0. You have the region between 0 and 1, the region between 1 and 2, between 2 and 3, and so on. So at the end, you have 7 regions. Again, more details about this can be found in the paper by LORENE and collaborator 2009. But this is why there are only 6 values for the density, because you use these 6 values, and at the end you get 7 regions. Another thing that I didn't mention, that Iosomni can use what is called an hybrid equation of state, in which on top of the piecewise polytropic equation of state, you also can add a thermal component in order to mimic some finite temperature effect. Piecewise polytropic equation of state, as Atul said, described cold equation of state, which is very good for the spiral. This is not good after merger, because during merger temperature may rise a lot and may become important for the evolution of the post-merger remnant. So by adding a thermal component via simple gamma law, you may try to mimic some of these thermal effects. And this is what we are doing with this line, which are adding a gamma law with a gamma thermal of 1.8, following a suggestion that was made by Otto Kezaka and collaborators in 2013. And I think it is one of the most used values. Then we go on, we have the parameter for GR hydron. And here we are saying that we want to use an equation of state of type general, which means that the pressure is a function of both rest mass density specific internal energy, and that we are going to use this hybrid, that they say the equation of state, which means you have a piecewise polytropic equation of state that describes quite well the cold part of an equation of state. And then in order to mimic temperature effect, which are important in merger and post-merger part, we add on top of that a gamma law. And if I remember correctly, that should it from the point of view of reading initial data. This is all you need to set in order to read the initial data. So we can execute this file in order to create this parameter file. Okay, so this parameter file is going to be created. Remind you that you are inside your Cactus directory, and we are going to create this directory inside the par subdirectory in Cactus, where usually you want to keep your parameter file. That is not compulsory, but we do that way in order to keep it tidy. Now we're doing something similar to what we did yesterday. So we create the simulation, and this is the first command using SimFactory. I call the simulation BNS_18. I execute this first line in case, for example, you already run the simulation, you remove the old files in order to start from 0. That is useful maybe for me because I already did this. So let's do this. You provide a name of configuration, the standard name sim, and the parameter file, which is the one we already created. I remind you that we are within the Cactus directory. So we execute this cell. Okay, everything went well. So it creates the directory where the output is going to be produced. Okay, home, in my case, home, Jackman simulation BNS_18. In your case, should probably be home, your username, simulations, and so on. And now we can submit the simulation. When I'm using the server by myself, it was taking 2 minutes. Let's hope it's not too long because it's just going to read the initial data, produce output, and then quit. Okay, so we can start the simulation. I execute this in just one core, okay, and one operating thread. So we start the simulation. Okay, so it was submitted successfully. And if you want, you can have a look at the output while the simulation is running. This is the same things that you did essentially yesterday during the tutorial. I can show the output. Okay, let me take auto scroll to bottom so I can go up. Okay, this should be the standard error. This is the standard output. So just information about the grid, so on. So this time probably should start reading the data. Anyway, we'll have a look at this later. You can also monitor the status of your simulation with the following cell, list the simulation. If you did the tutorial yesterday, you should probably see, as in my case, hello world and TV_ET, which were the tutorial made yesterday, that were run probably yesterday. We are running now. Okay, and say they're still running. Are there any questions up to now?
There's none in the chat.
I'm monitoring the chat, yeah, in case there is anyone. Or is anyone having problems in following this notebook?
You made it work too well, it looks like.
No, well, no, you talk too early.
No, I'm joking.
No,
somebody
because
got,
I just saw now a message in the chat.
Yeah, somebody got a signal 9. Signal 9 looks like some kind of load error. If you got that, if you're the person who got that signal 9, maybe run the application and see if you get it again.
This should also run on any laptop without any problem because it really requires a very small amount of memory.
Right. It looks like, though, Bruno, it looks like what happened is, I'm just looking at the system. Okay. We have 251 gigabytes, but we have 102 students. And I think that in addition to running your thing, they're running something else. I am going to see if I can get our memory increased again.
Okay, thanks.
It won't happen during your talk, unfortunately, but for the rest of you, I'm going to try and get something. I'm going to try to increase our memory beyond 250, which I thought was enough.
Yeah, there are too many people. It's been too successful. I mean.
Yes, but I guess it's a good sort of failure to have in a way. So, okay.
Yeah, too many people is always a good.
Sorry, Bruno, I just wanted to confirm that even running locally, it is very, very fast. I'm running it on my laptop and it was very quick. Maybe
okay, thank you very much.
If somebody wants to switch from the Jupyter server to the laptop, if they have you know, Cactus and so on.
Yeah, and they need to have Cactus compiled. And then I can just download the notebook. As I said, I put the notebook also in the abstract. So if you go to the abstract on my lecture, you find the notebook. Meanwhile, I wanted to show you this. This is the standard output. Okay, it's usually a Cactus prints a lot of information. And so at this point is printing information, for example, regarding the Bedon_bin_ns equation of state. In particular, it's saying, for example, that is reading from file home Giacomo etk school 2021 result.d as a specified parameter file. And then what is printed later, this is stuff that comes directly from the LORENE library, because when you compute the Einstein Toolkit, you compile the Einstein Toolkit also together with the LORENE library. In this case, there is LORENE library that comes within the Einstein Toolkit. And so this information are essentially printed by the LORENE function that is going to read this file And therefore it prints out some information, and this should correspond to the information in principle that you get when you generate the initial data file. Okay, so for example, you see that the initial data were generated with an equational state that was a kind of piecewise polytropic equational state with 7 polytropes. And then you have the different value of gamma, which is a dimension, and kappa in Lorentz units of gram per cubic centimeter. Okay, this is K0, the one we needed to convert then for Yosomi, and so on. And then you have the other regions, 4, 5, 6, start from 0. So as you see, you have 7 regions. Then, as Atul mentioned, in the power_1D, you also have, for some reason, I'm not sure why, or maybe they get it for, well, anyway, you also have the pressure at one of these regions. I don't think this is really needed. Indeed, the Yosomi does not require for the value of this pressure. Then you have the divided density in logarithm base 10 in CGS, okay? And then there are some things that I'm not going to the details, but it's just how to get it produced by the LORENE libraries, while the Einstein Toolkit Torn is reading the initial data. Okay, so in principle, all these outputs should correspond to the output that you get when you run, for example, the program call in LORENE. If they don't correspond, then it means that you're probably loading the wrong initial data. So it's always a good idea to check the standard out in order to be sure that you're actually loading the correct initial data file, and you are not loading by mistake some other file, some other initial data configuration. It's also good to see that there are no nuns because it means that the data are fine, the file was not corrupted. Okay, so all these are LORENE information. Let me see, should I finish that? Okay, yes, in my case it's finished. Okay, so let me refresh also this one, the show output. Okay, and as you see, so I finished reading this all LORENE information up to here, and then there is some information that are printed by Torn, but done by being NS, with some information about the initial data that you read, and it also say done, which means it was able to import the initial data without any problem. Then there's some other information. This is statistics from CarpetLib. Yeah, I don't know how much this number can be trusted. To be honest, I never understood this, to be honest, how much I should trust this number from CarpetLib. But here, as far as I understand, it says it is using 4 GB of RAM. Okay. Then it prints this line for iteration 0, and then it stops because we told to the Einstein Toolkit to just stop at iteration 0. We just want to save the initial data in order to have a look at them. And in order to do that, what we are going to do is to use Qubit, which will be a topic of the next talk. So for Qubit, you can ask questions also later, but essentially is a Python library that can be used to read data produced by the Einstein Toolkit. This is not the only Python library. There's also another Python library developed by Wolfgang Karstan, which is called PostCactus, which is also very nice. And by the way, Qubit was based on PostCactus. I decided to use Qubit since the talk after me is about Qubit. So I decided to use it just to show an example. But the data that are produced by the simulation, as I said, can also be opened, for example, by using PostCactus by Wolfgang Karstan. Or otherwise, you can also use other visualization program like Visit, which is a very simple program to use. It's based on a graphical user interface, so it's very user-friendly. But if you want to produce figures for papers, I recommend that you use these Python libraries, for example, Qubit or PostCactus. So what I'm going now is just to load the Matplotlib, NumPy, well, NumPy I think I already loaded before, and Qubit. Now here we are, I remind you, we are still in the Cactus directory. I'm going to use SimFactory in order to get the directory where the output was saved for our simulation. And this is the command in this cell. Okay, and so it says that in my case, the outputs were written in home, the Giacomo simulation, BNS_ET, output-0000. See, these are where the data are saved. And now we're using Qubit. Qubit in particular has a function called seen here, where you can pass essentially the location of the directory where your data are saved, and then you can extract all the green functions that were saved in the output. And this is the command that is executed in this cell. So this comes from Qubit libraries, this seen here. You have essentially the same functionality also in PostCactus. So in phase that is looking at this directory and doesn't find any data in 1D, and that is fine because in our parameter file we didn't ask for any 1D output, but instead it finds quite some output in 2D. So here I list all the variables that are available in 2D on the XY plane, XZ plane, and YZ plane, and even asked for a few variables in 3D. In this case, the rest mass density, rho, the lapse, alpha, and the specific internal energy epsilon. Particularly here, we are creating essentially two lists, one for the 2D variables that were saved on the XY plane and the 3D variables. Here it is. Okay, so I have this vars 2D, which contain now only the green function that were saved on the XY plane. And again, here I have the list. And vars 3D are the variables that are saved in 3D. To keep things simple, we are going just to have a look at the rest mass density in 2D. So this is the command to load the mass density and create a variable underscore rho underscore b. And then normally you also have to select the iteration that you want to visualize. In this case, we only have one iteration. So I create this variable rho 0, which is equal rho b at iteration 0, which is the only iteration we have. This can be also seen by this print statement, where I ask to print all the iterations that are saved, that are available for the rest mass density. And in this case, you see it returns just 0. It's only iteration 0 because we stop at iteration 0. And then another couple of print statements. By the way, all these blocks that regard Qubit are just copied and pasted essentially from the Qubit tutorial. So Qubit has a very nice tutorial online, you can follow it. So here I'm just following the standard Qubit tutorial, just using this data that we produce for binary PostCactus. And then we want to do a visualization. And so we want to have a look at the response density on the equatorial plane. And this is what is done in the next cell. And here it is. We see the two neutron stars, one on the right and one on the left. This is an equal mass system, so the two neutron stars are identical. Here you have the scale in log 10. And it is already, no, it's not converted to GGS. This is still in Cactus unit, sorry. More information on visualization can be asked to the next speaker, since he's going to speak about Qubit.
Why is the surface looking so irregular?
This is a question I think more because I had a look at this data with visit. So this is a question for the next speaker, because what Qubit does, at least this I got from the tutorial, that instead of plotting the rest mass density directly on the original grid, it needs to create first a uniform grid and then interpolates on the uniform grid. So I think these are errors on interpolation. Because if you open this data with visit, you will see a sort of two LIGO stars, because these are very, very coarse resolution. So I think all this stuff is just interpolation done by Qubit.
So in principle, if you used a higher resolution uniform grid, you could get something smoother.
Don't think, well, I can try, I mean, if I put, but I don't think so, because I think I tried, but let me see.
I think the statement is that the source data, the 3D data, is really coarse. If visit shows you Lego cubes.
Oh, I see.
Exactly, that is what, yeah, exactly. While Qubit wants to interpolate, so actually I have a question. If the speaker, I think I saw him connected, but if there is a way for Qubit just to plot the data in the actual mesh, the one that was used, and not by interpolating in a uniform grid, because with visit I can do that.
Yeah, so what you can do is you can, so I think by default, a multilinear interpolation is performed. So that's probably why you see this. If you want to plot with a nearest neighbor interpolation, so essentially you still have to have a uniform grid, because like an image is a uniform grid of pixels. So in Qubit, everything is done on uniform grids when you plot. but you can switch on nearest neighbor interpolation. So you'll have a LEGO instead of this artifact. So now I don't remember exactly how you do it because I typically do it in a different way.
Okay.
But we can discuss that later.
5 minutes.
Okay. So I see a question that is a very interesting question in the chat about the baryon mass and gravitational mass. In Lorene, we use baryon mass, but how we know it's a gravitational mass? That is a very excellent question. So what I typically do for binary neutron star, I first use Lorene, for example, to generate a sequence of TOV solution for my equation of state. This can be done by code which is within Lorene, which is called ROTSEC, which is within NROT star. Let me type the name of this code in Lorene. And it should be ROTSEC. This is the directory codes within Lorene. So I first solve the TOV equation. I get my sequence of TOV. And the Lorene gives me for the sequence of TOV both the baryonic mass and the gravitational mass, as well as the central enthalpy, or to be more precise, the logarithm of the central enthalpy for that particular model. So let's say that I want to build a two neutron star that have 1.36, 1.36 solar masses, and this is the gravitational mass. When I say this, it means that each neutron star infinite separation should have a gravitational mass of 1.36. I pick up these masses because these will be the masses corresponding to GW17 or H17 if that was an equal mass system, for example. So I compute the TOV solution. I look what is the value of the central enthalpy for a gravitational mass of 1.36. And then actually in Lorene, when you want to compute the initial data for a binary neutron star system, you provide that value for the central enthalpy. And so Lorene is going to build you a binary neutron system which has the same baryonic mass of the star you had in your TOV solution. This is how you need to proceed essentially. Because if you get the gravitational mass that Lorene provides you from the computational binary, that is not going to be correct, as well as the one you get from the Einstein Toolkit, because when you compute the gravitational mass, of course, you take into account also the gravitational potential. And when you have a binary, of course, you also have the effect of the gravitational potential, which is star on the other. So as I said, usually I proceed in these two steps. First, I generate a sequence of TOV. And then by looking at the central enthalpy of the TOV I want to evolve, I use that in a bin star in order to compute the binary. Before we close, I just wanted to mention that if you go back to my abstract, a few hours ago, sorry about that, I put a parameter file. This cannot run on a laptop. It's quite expensive. It needs to run on a cluster, but it's a more complete parameter file for those of you that would like to do an evolution actually with this initial data. Okay. So if I download it and I open it with a text editor, I have probably to change because now you don't see it. Sharing very quickly. If you find it, okay, it is. Okay, now you should see it. So this is the parameter file. It's more complex than the one I showed you before. The part regarding Eosomni, the reading initial data is really the same. What changes is the grid setup and evolution, as well as the output and so on. But this is a parameter file that you can use as an example if you want to do an evolution. So for example, the grid is much more extended. You see that it goes from minus 1,920 to 1,920. This is the resolution on the clusters level. I'm using actually 7 refinement levels. Therefore, the resolution, the finest level will be 0.12. Here there is the grid setup. Here I'm actually activating only 6 levels instead of 7 in order to save a bit on memory. And essentially, if you keep the parameter file as it is, will be like a fixed mesh refinement simulation, in which the neutron stars are contained into a box with a radius of 35 on the equatorial plane and 24 on the Z plane, and with a resolution 0.24. So will be good enough to have a look at the qualitative evolution. If you want to do something more quantitative, then you have to remove this comment, which means changing the 6 and 7. And this will add 2 smaller boxes, each around each neutron star with a resolution 0.12 cactus units. And these boxes will actually move following the neutron star using a torn, which is part of the Einstein Toolkit, which is volume integral. That here is commented, but I put some information, okay? Uncommented falling lines to have the moving boxes. But if you keep everything commented like it is, as I say, it will be run in fixed mesh refinement, in which the neutron star will be in just one box with a resolution 0.24, and that will be enough to get a qualitative idea of the evolution. And just last thing I want to mention, and then I stop. I don't see the chat anymore. Okay, I lost the chat. I think there was something posted in the chat, but for some reason. Let me see if I can. Okay, okay. I think I answered this. The other things about this parameter file,
5 minutes.
It's that I added this block about the outflow torn. This is very useful to compute things like, for example, if after the merger you produce a black hole, this is going to compute the accretion rate onto the black hole, and this is given by these 2 lines. And I also added some surface in order to compute, for example, the amount of matter that is ejected from the system. That could be useful, for example, for kilonova estimation. Okay, so for those of you that are more adventurous, I think this parameter file can be used for evolution. As I said, this is something I'm not going to run on a laptop. It's not going to run on a workstation. You need to run it on a cluster. Possibly, if you change a bit the domain, for example, at the moment I'm using quite large domain. If you reduce the extension of the domain, maybe you can fit on a very powerful workstation, but very powerful, I think 64 GB of RAM, something like that. But this is, let's say, a more complete example for those of you that would like to do actually an actual evolution and not just read the initial data.